So this is a video going through the practice sheet 10, which we didn't have time to do in the class. So first of all, let me tell you what is and is not going to be on the exam. We saw in this week there were various topics. The first one is about finding the gradient in more than one dimension. Then there was Taylor series in more than one dimension, second derivative test in 2 dimensions, and then these things about changing coordinates. So the Jacobian matrix, Jacobian determinant, and then change of variables and integrals. Okay, sorry, you can't see that, but anyway, that's what it was. So in terms of the exam, because we didn't really have time in class to do this in detail, I've decided it's unfair to ask you to do all of this in the exam. So I've decided on the exam is only going to be the first 3 things. So questions 1, finding the gradient. Question 2, finding Taylor series. These will be quite simple, so don't worry too much about that. And question 3, using second derivative test. These may be on the exam. The other stuff, so the things about Jacobian and so on, they will not be on the exam. Okay, but in this video I'll still show you the solutions because I think it's interesting and you may well have to use it later on in your physics careers, so I'll explain everything. Okay, so we start with question 1. That's very simple, just find the gradient. Okay, so 1, find the gradient of the following functions. So the first one is A, find the gradient of the function cos x sine y. Okay, so the first component is just differentiate with respect to x. So that gets you minus sine x sine y. And the second component, differentiate with respect to y. That gives you cos x cos y. Okay, so that's the answer. Pretty easy, right? So the formula here is grad f is df by dx, df by dy, and then df by dz or whatever, depending how many variables you got. Okay, the next one, the function is again 2 variables, x log y plus y log x. So the first coordinate is differentiate with respect to x. That gives you log y plus y over x. Second coordinate with respect to y, that's x over y plus log x. Okay. C is this gradient of the radius, basically the radial vector x squared plus y squared plus c squared. So this is just the length of the vector x, y, z, right? So first you differentiate with respect to x, so that gives you 1 over 2 square root x squared plus y squared plus c squared times the derivative with respect to x, which is 2x. Okay, and then the same 2y over the same thing, 2z over the same thing. Okay, so you can simplify this as just, you see the factors of 2 cancel, right? So this gives you x over r, y over r, c over r. Okay, you can leave it in this form, but using the fact that r is just that gives you a simple way of writing it. Okay, and finally the last one again has 3 variables, y e to the x c. Differentiate with respect to x, that gives you y c e to the x c. Differentiate with respect to y, that gives you that. And differentiate with respect to z, that gives you that. Okay, so that's the answer to question 1, so I think that hopefully was not too difficult. Okay, question 2 is about finding Taylor series. So in particular, as for Taylor series up to length x cubed. So this means you have to find the terms up to the cubic terms. So what this means is, for example, x cubed or y cubed or x squared y or xyz. Like, these are all terms of order x cubed, right? Something cubed. So the first one is f of xy is sine x minus y. So that's quite easy because you should know that the Taylor series of sine x, right? So Taylor series of sine x is equal to x minus x cubed over 3, and that's all you have to do because you only have got to x cubed. So therefore sine x minus y, it's just change x into x minus y. So x minus y minus x minus y cubed, sorry, 3 factorial over 3 factorial. Okay, and that's the answer. Okay, so that was pretty easy. The next one is a little bit more tricky. E to the x over 1 minus y. Okay, so here you need to use the 2 Taylor series for e to the x. X cubed over 6, and so on, only up to x cubed, and also for the y, so 1 over 1 minus y, that's 1 plus y squared plus y cubed, and so on. Okay, and then here you just multiply them together, right? So this is 1 plus x squared over 2 plus x cubed over 6 times 1 plus y squared plus y cubed, and so on. Okay, so putting everything together, the constant term is just 1 times 1. The linear terms is just x from here and y from there, so x plus y. The second order terms, the squared terms, is x squared over 2 from there, then xy from there, and then y squared from there. And finally, the cubic terms are x cubed over 6, x squared y over 2, xy squared, and y cubed. Okay, so that's the answer to that. And part C is actually very easy, although the function looks complicated. So this one is log 1 plus xy over 1 plus x plus c. Okay, so here again, you just have to use the 2 Taylor series. Log of 1 plus xy, this is equal to xy minus xy squared over 2 plus, and so on. So this is already a term of order 4, right? It's x squared times y squared. So you can ignore the higher terms. And then you've also got 1 over 1 plus x plus c. This is 1 minus x plus c plus x plus c squared, and so on. So you have to multiply those together. xy minus xy squared over 2 times 1 minus x plus c plus x plus c squared, and so on. So the lowest order term here is a squared term, so term of order 2xy. And then the next term here is a term of order 3. So minus this times that, so that gets you x squared y plus xy c. Okay, and all the other terms have higher orders than that. So that's the answer to that one. Okay, now number 3, use the second derivative test on these functions in 2 variables. So let me just quickly remind you what the second derivative test is in 2 dimensions. Okay, fxy has a local minimum at xy if the following conditions are met. The first thing is that the first derivatives are 0. The second thing is that the second derivatives in x or y, or both, well in fact it will be both, but anyway, the second derivatives should be greater than 0 for a local min. So those two parts are the same as in one dimension, there's nothing different there. But the third condition you have is something new, which is relating the mixed derivatives. And what it says is that this thing, d2f by dx dy squared minus d2f by dx squared times d2f by dy squared, this thing should be less than 0. And this is what ensures that the second derivative is positive in every direction. So these are the conditions for a local min, and conditions for a local max are very similar. In fact, the first and third conditions are the same. So the first condition is, again, derivatives are 0. Second condition is that the second derivatives have to be negative for a local maximum. And the third condition is that, again, this thing is negative. Okay, so that's your second derivative test in 2 dimensions, and now let's use it on these functions. So the first function, f of x and y, is x cubed minus y cubed minus 2xy plus 2. Okay, so I think I'll calculate all the derivatives first. So df by dx is 3x squared minus 2y. df by dy is minus 3y squared minus 2x. d2f by dx squared is 6x. d2f by dx dy is minus 2, and d2f by dy squared is minus 6y. Okay, so these are all the derivatives that we'll need. Okay, so first thing we need to solve is that df by dx and df by dy are 0. So when is that true? So that means this must be 0 and this must be 0. So 3x squared minus 2y equals 0, and minus 3y squared minus 2x equals 0. Okay, so we can use this one to get y as a function of x. So this means y is 3 over 2x squared, and then let's put that value of y in here. That gives you minus 3 times 3 over 2x squared squared minus 2x is 0. So simplify that, so that's 27 over 4 minus 27 over 4 x to the 4 minus 2x equals 0. So this is 27x, I'll multiply the 4 up, times x cubed plus 8 equals 0. So that means x equals 0 or x equals minus 2. The other solutions are not real to that equation. So there are 2 solutions to that, and let's see what y is from this equation. If x is 0, then y is 0, and if x is minus 2, then y is 426. Okay. So therefore the 2 possibilities we have are 0, 0, and minus 2, 6. Also, hold on, x squared, so we have 4, 2, 6. Okay, looks right. So now let's check the second derivative tests. So at 0, 0, the second derivatives are 0. d2f by dx squared equals d2f by dy squared equals 0. So that's not good. And also if we look at the condition 3, d2f by dx squared, dx dy squared minus d2f by dx squared times d2f by dy squared. These are 0. This one is minus 2, so this is 4, which is greater than 0. Okay, so therefore this is not a min or a max. This one. So the only other possibility is going to be this one. So let's see what that says. 2, 6. Okay, so I'll keep that there. So at minus 2, 6, the second derivative with respect to x is 6x, which is minus 12, so that's less than 0. The second derivative with respect to y is minus 36, that's less than 0, and d2f by dx dy squared minus d2f by dx squared d2f by dy squared, that's 4 minus 12 times 36, which is definitely negative. Don't really care what it is. Okay, so that means we have satisfied, in this second case, we've satisfied the conditions for a local maximum. Right? This is true, and that is true. So therefore this point is a local max. Okay, so right, so that's the end of the first one. So there were 3 altogether, so let's do the others. Part B is this function g of x and y, which is y minus log y times x minus log x. Okay, so as before, I'll work out all the derivatives first of all. So dg by dx is 1 minus 1 over x times y minus log y. dg by dy is 1 minus 1 over y times x minus log x. There's a symmetry, this function, right, which you can exploit. d2g by dx squared is 1 over x squared y minus log y. d2g by dx dy is 1 minus 1 over y times 1 minus 1 over x. And d2g by dy squared is 1 over y squared x minus log x. Okay, so those are all the derivatives we need to know. So first of all, we need to solve first derivatives as 0. Okay, so that means 1 minus 1 over x y minus log y equals 1 minus 1 over y x minus log x equals 0. So it means that one of these are 0, right, in each case. So this one is 0 when x equals 1. This one is 0 when y equals log y. That does not have solutions, right? And this one again is equal when y equals 1. This one does not have solutions. So your only solution is the point 1, 1. That's the only possibility. Okay? So at the point 1, 1, we have to work out the higher derivatives. d2g by dx squared is 1 times 1 minus 0, which is 1. d2g by dy squared is also going to be 1 because it's symmetrical, right? And d2g by dx dy is this one, that's 0. Okay, so therefore d2g by dx dy squared minus Da, da, da. Okay, this is 0 minus 1 times 1, which is minus 1, which is less than 0, right? So we've got this one is less than 0, these are greater than 0. So if you go back to our conditions, that's the condition for a min. Right? These are greater than 0, this one is less than 0. Okay, so therefore this point 1, 1 is a local min. Good. And then we have to do just the last one. Same kind of method. So this one is the function h, which is x minus 1 times e to the minus y squared plus x squared. So let's work out the derivatives. That is e to the minus y squared plus 2x. That is minus 2y, x minus 1, e minus y squared. That is 2. That is, differentiate that, minus 2y e minus y squared. And that's differentiate that with respect to y. That's a bit more tricky. So I'm going to get minus 2 lots of that. And from here I'm going to get plus 4y squared. So 4y squared minus 2 x minus 1 e minus y squared. Okay, so those are all the derivatives. So first of all, when are these first derivatives 0? Okay, so if I look first at dh by dy equals 0, that's this. There's only two possibilities, either that's 0 or that's 0. Right? So either y is 0 or x equals 1. Okay. And if I look at the first derivative, if I look at this one, y equals 0, then you get 1 plus 2x. That gives you x is minus a half. So that gives you the point minus a half, 0. And if you look at the dh by dx when x is 1, that gives you e to the minus y squared plus 2 equals 0. This has no solutions, right? Because it must be positive. So your only possibility is this one. So now we work out the second derivatives at this point. So this one is a constant. This one is, so y is 0, so that's going to get you 0. And d2h by dy squared. That's this one. If y is 0, you get minus 2 times x minus 1, so that's minus 2 times minus 3 over 2 times 1, which is 6. Okay, so these are greater than 0, so it looks like it's going to be a minimum again, and we just have to check that d2h by dx dy squared minus d2h by dx squared d2h by dy squared. This is 0 minus 2 times 6, which is minus 12, less than 0. Okay, so we have satisfied our conditions again for the local minimum. First derivative 0, second derivative is positive, and this is true. Okay. So therefore this point is a local minimum. Okay, so that's the end of question 3. And as I said, those 3 questions are all that's going to be on the exam. Okay, but let me do the rest anyway for your benefit. So questions 4 and 5 I'll take together. These are looking at the Jacobian matrix and change of coordinates. So again, let me just remind you what that's about. Suppose that you've got some function f in the coordinates x and y, and you want to express it in some other coordinates f of u and v, where these coordinates u is some function of x and y, and v is some function of x and y. Okay, so the classic example of this is going from Cartesian coordinates into polar coordinates r theta. Okay, but it doesn't have to be that. You can make any change of coordinates you like, provided that these two fix these two, and vice versa. Okay. And the formula you got, which uses the Jacobian, tells you that the derivatives df by du and df by dv, this is the generalization of the chain rule, should be equal to dx by du, dy by du, dx by dv, dy by dv, times df by dx, df by dy. Okay, so this is the generalization of the chain rule to two dimensions. Okay, so for example, df by du is df by dx, dx by du, plus df by dy, dy by du. Okay. There's a kind of intuitive explanation for why this is. Let me just explain it. So suppose my x and y coordinates look like this, and then suppose at this point here I'm looking at, suppose that my u coordinate is going off in this direction. Okay, then df by du is telling me what happens to f as I go along this direction, right? And obviously that's a combination of what happens to f if you go along the x direction, plus what happens to f if you go along the y direction. Okay, so it's a combination of df by dx, that's this part, and df by dy, that's that part. Okay, so it kind of makes intuitive sense, this formula. Okay, so now with that we can solve the question. So in this I tell you that you've got the functions x, well, okay, in this case I tell you the inverse functions. So x, u, and v is uv, and y, uv is a half v squared minus u squared. Okay, so we can use that to find these derivatives in the Jacobian matrix. So this is called J Jacobian matrix. Okay, so let's work out those derivatives. So dx by du is just v, and dy by du is minus u, and dx by dv is u, and dy by dv is v. Okay. So therefore the Jacobian matrix is v minus u, u, v, and determinant of the Jacobian matrix is v squared plus u squared. Okay, nice. That's part A. Part B asks you to use this formula for the partial derivatives to calculate, in this case, for the function f of xy is log x squared plus 2y minus 1. Okay, so if we're going to use this formula, we need to find derivatives with respect to x and y. So df by dx is 2x over x squared plus 2y minus 1. df by dy is is 2 over x squared plus 2y minus 1. So therefore, put it in the formula, df by du, df by dv, is Jacobian matrix times df by dx, df by dy, okay, so this is going to get you 2xv minus 2u over x squared plus 2y minus 1, and this one 2xu plus 2v over x squared plus 2y minus 1. Okay, and it's probably better if you write this all in terms of x and y, or all in terms of u and v. So we know how to write x and y in terms of u and v. So let's work out what that is. Let me just do it up here to fit it all in one place. So here you've got 2xv minus 2u. So x is just u times v. So this is 2uv squared minus 2u. So this is 2uv squared minus 1. And on the bottom you've got x squared plus 2y minus 1. This is uv squared plus v squared minus u squared minus 1. That's u squared v squared plus v squared minus u squared minus 1. Don't think we can do anything with that. No factorize. Probably does, doesn't it, right? V squared u squared plus 1 v squared minus 1. That will work. Well, next time we'll get v squared u squared plus v squared minus u squared minus 1. Okay, so that's v squared minus 1 times u squared plus 1. Okay, and then finally this one, 2xu plus 2v. This is 2u squared v plus 2v. So this is 2v 1 plus u squared. Okay, so putting all of that into here, this gives you, in terms of u and v, 2u v squared minus 1 over u squared plus 1 v squared minus 1. Okay, so they nicely cancel, and here you get 2v 1 plus u squared over u squared plus 1 v squared minus 1. Again, they nicely cancel. So the final answer is 2u over u squared plus 1 and 2v over v squared minus 1. There we go. Okay, so that's the end of question 4. Question 5 is looking at spherical polar coordinates. So if you, I guess you've seen these, but just to remind you, this is a way you can measure coordinates in the x, y, z plane using a sphere, as the name suggests. So if you have a vector somewhere up here on the sphere, so it hits the plane there, then the radius vector is r, the angle here is theta, and then the angle of the vector projected into the xy plane, this angle here, is usually given the symbol phi. Okay, so these are the spherical polar coordinates r, theta, phi. Okay, and in equations they are x is r sine theta cos phi, y is r sine theta sine phi, and z is r cos theta. Okay, so this question is only asking you to find the Jacobian matrix. So that's going to be these derivatives here, dx by dr, dx by d theta, dx by dr, dy by dr, dy by dr, and dz by dr. So the bottom coordinate stays the same in the rows. Then dx by d theta, dy by d theta, dz by d theta, and finally dx by d phi, dy by d phi, dz by d phi. Okay, so you have to work out all those derivatives. So they're not hard, there's just 9 of them. So dx by dr is sine theta cos phi, dy by dr sine theta sine phi, dz by dr cos theta. Dx by d theta is r cos theta cos phi. Then here you've got r cos theta sine phi. Here you've got minus r sine theta. And then by phi, r sine theta minus r sine theta sine phi, r sine theta cos phi, and 0. Okay, so that's the Jacobian matrix. You also ask you to calculate the determinant of the Jacobian matrix. So let's just expand in this row here because we've got a nice 0. So that's plus and minus chessboard. So that's going to get you cos theta times the determinant of r cos theta cos phi, r cos theta sine phi, minus r sine theta sine phi, sine theta cos phi, plus r sine theta times the determinant of this matrix, sine theta cos theta, sine theta sine cos phi, sine theta sine phi, minus r sine theta sine phi, r sine theta cos phi. So this is cos theta times, so you get r squared, you can see right, r squared, cos theta sine theta, and then you get cos squared phi plus sine squared phi. So it's going to be cos theta sine theta, and then cos squared phi plus sine squared phi. That's that one. And here again you get another r, so you get r squared sine theta, and here you get sine squared theta, and phi's are cos squared phi plus sine squared phi. Okay, so this is 1, this is 1, and then you've got a sine theta you can take out, so you get r squared sine theta, and this is cos squared theta, this is sine squared theta, so the final answer is just r squared sine theta is the determinant of the Jacobian matrix. So remember what this means is, how does the volume change? If I have a little cube which has the volume dr, d theta, and d phi, then the volume of this cube is equal to dr, d theta, d phi times the determinant of the Jacobian matrix. Okay, so this is r squared sine theta dr, d theta, d phi. So you may have already known this result. When you integrate something in spherical polar coordinates, instead of just integrating dr, d theta, d phi, you have to multiply by this r squared sine theta. Okay, and the meaning of this is that the volume of dr, d theta, d phi, and it comes from the determinant of the Jacobian matrix. Okay, so that's the end of question 5. So just 2 left, and these last 2 are on change of integration coordinates. So let me just give you the formula we worked out. Right? So the formula was that if you want to integrate a function f and x and y, dx, dy, and you want to change this into an integral over the function u and v, du, dv, then you need to multiply by something here. And the thing you need to multiply is the change in area between dx, dy, and du, dv, and that turns out to be the determinant of the Jacobian matrix from x and y into u and v. Okay. So when you make a change of variable like this, you have to multiply by the determinant of Jacobian matrix. Okay. So in question 6, the integral in question is this one. X squared plus y squared over 1 plus x squared minus y squared squared e to the minus xy dx dy. Right, so it's an absolutely horrible integral in x and y. So hopefully you can find some variables which make it easier, and it tells you that u is x squared minus y squared and v is 2xy. Okay, so as I've given it here, the thing that you can easily work out is the Jacobian matrix from uv into xy, i.e. the opposite of this one. But they're related in a simple way, which I'll explain in a minute. Okay, so let's first of all calculate this Jacobian matrix. So this is du by dx, dv by dx, du by dy, dv by dy, which is 2x, 2y, minus 2y, 2x. Okay, so therefore the determinant of this Jacobian matrix is 4x squared plus y squared. Okay. Now, as I said, it's not quite the matrix we want, because we wanted the matrix from xy into uv. And what we found is the matrix from uv into xy. But it's hopefully not surprising that these are inverse matrices of each other, right? Because if you do one and then the other, that's the same as going from xy into uv and then back to xy. So that should be the identity matrix, right? So in other words, j of xy uv times j of uv xy, this should be the identity matrix. So this means that j xy uv is just the inverse of j uv xy. And we know a nice formula about the determinants then. The determinant of j xy uv is equal to 1 over the determinant of j uv xy. And this is the theorem we proved. The inverse matrix has 1 over the determinant. We've calculated the determinant, so this is 1 over 4 x squared plus y squared. Okay, and that's good because you notice x squared plus y squared is going to cancel this one up here. So that already shows we're on the right track. Okay, so the only other thing which is tricky is we have to think about what values should we put for u and v here. So if you think about what this looks like, x and y are going from 0 to infinity, so that means you're integrating this quarter of the plane here. So what values of u and v should be taken there as x goes from 0 to infinity and y goes from 0 to infinity? Okay, so from here you can see that v can be anything from 0 to infinity itself. Right? So v goes from 0 to infinity, and from here, if I go along the x-axis, then u is just equal to x squared. So that goes from 0 to infinity. And as I go along the y-axis, it goes like minus y squared. So that goes from 0 to minus infinity. And therefore, okay, so therefore you need to take, if x goes between 0 and infinity, and y goes between 0 and infinity, then that's the same as taking v between 0 and infinity and u between minus infinity and infinity. You can check there's a one-to-one correspondence between points here and points here. Right, so now let's put all that together in our formula for I, and hopefully we'll get an integral that we can do. So I is the integral from 0. I'll just write it out again first of all. Y. Okay. So what do we use here? So we use that u is x squared minus y squared. V is 2xy. We know that the determinant of the Jacobian matrix from xy into uv was 1 over 4 x squared plus y squared. Okay, so we get the integral of x squared plus y squared over 1 plus, so this is u squared on the bottom, then this is e to the minus v over 2 times the Jacobian, so that's 1 over 4 x squared plus y squared. So you see that they cancel. And then integrate du dv, and we decided u should go from minus infinity to infinity, and v should go from 0 to infinity. Okay, so you see that this nicely separates, right? U only depends upon the first term, and v only influences the second term. So this whole thing is equal to the integral from 0 to infinity, v to the minus v over 2 dv, times the integral from minus infinity to infinity of 1 over 1 plus u squared du. Okay, so this is 2e minus 2e to the minus v over 2 between 0 and infinity, and this, you know, is arctan, right? Minus infinity, infinity. So this is just 2. As u goes to infinity, arctan goes to pi by 2. As u goes to minus infinity, it goes to minus pi by 2. So that gives you pi. So the answer is 2 pi. Okay, so you see here we managed to integrate a fairly hideous, very ugly function of x and y, and we did it by making a change of variables into uv. We made use of the Jacobian formula there. Okay. So finally we've got question 7. So this is just showing you a physical application, and this is what you'll probably learn in one of the mechanics classes if you haven't already. This is about the center of mass. So center of mass is quite a simple idea. You have some shape in 2 or 3 dimensions, and you want to know where is the point on that shape at which it will balance. So where is the point on that shape, which is the center of the mass. Okay. That's where the word center of mass comes from. So it's defined as the average over the shape of position weighted according to the density. So that's this integral here. You integrate over the shape of the position of the point on the shape multiplied by the density of the shape at that point. Okay, and if you integrate that over the whole shape, area or volume, and then divide by the mass, this was a mistake in the original worksheet, it should divide by the mass here, then this gives you the center of mass. Okay, so this is a physical thing, but this is really just to give you practice of integration and changing variables of integration. You see the 4 shapes I ask you to do here. There's a clear choice of coordinates for each of them, right? So this one is a semicircle, so it makes sense in this case to use the r theta coordinates in part A. Part B is a sphere, so it makes sense to use the r theta phi coordinates for this shape, and again for this one as well. It's another sphere. And then D here is a cylinder. In this case, I haven't talked about these coordinates, but you can use cylindrical coordinates. So these are coordinates which measure height z in this direction, radius r here, and again angle theta, like this. So in part A we'll use r and theta, in parts B and C we'll use r theta phi, and then in part D we'll use r theta z. Those are the coordinates for the integration, and you'll see how that makes this integral much easier. Also note that these shapes have a lot of symmetry, right? this one is symmetrical around the axis, this one too, this one too, and this one too. So that means wherever the center of mass is, it's going to be somewhere on this line, right? Because it's symmetrical. And therefore, we only need to worry about the position in one direction, right? So although the center of mass is a vector, we only care about the component along this axis here. Right, so that's a bit of motivation and information. So we'll start with the calculation now. Number A, letter A. Okay, find the density, find the center of mass of this semicircle. Okay, so we're going to use, as I say, coordinates. This is R, and let's say that the maximum radius is capital R, and this angle is theta. So you see theta goes from 0 to pi. So let's call this direction the z direction, and then you'll get ZCM, the center of mass in the z direction, is 1 over the total mass times the integral of the density, which is a constant, times the height z, times integrate dr d theta. Okay, and r goes from 0 to capital R, and theta goes from 0 to pi. Now here, the thing you need to multiply by is the volume element, dv, and as we showed in one of the lectures, in radial coordinates, this is r d theta, r dr d theta, so we need to multiply by r here for that. And you also notice in terms of these coordinates, z is r sine theta, this triangle here, right? See. So this then is 1 over the mass. So what's the mass? The mass is equal to the density times the area, and the area is pi r squared over 2, so that's the mass. So you get 2 over rho pi r squared, integral 0 to pi, integral 0 to r of rho times z, which is r sine theta, times r dr d theta. Okay, the rho's cancel, and you see that the theta integral can be separated from the r integral. So this is 2 over pi r squared times the integral from 0 to pi of sine theta d theta, integral from 0 to r of r squared dr, which is sine integral of minus cos theta, 0 and pi, and r cubed over 3 between 0 and r, 2 over pi r squared times 2 times r cubed over 3, which is 4 over 3 pi times r. Okay. So that's the center of mass of the first one. Okay, so this turns out to be about 0.4. So it's about 0.4 of the way up the shape. Okay, so that's part A. Part B, we're looking at the hemisphere. So like this. Okay, and again, we're interested in the height z here. And you've got r and theta and phi going around this way. So ZCM is 1 over m times the integral of density times the z coordinate times the volume element, and this is what we worked out in question. Where is it gone? Anyway, I can't find it. Oh yes, here it is. In question 5 on this, we worked that the Jacobian determinant is r squared sine theta. So that means in spherical polar coordinates, dv is going to be r squared sine theta dr d theta d phi. Okay. So here you need to multiply by r squared sine theta dr d theta d phi. Okay, and r goes between 0 and capital R. theta goes from here 0 to pi by 2. And phi goes all the way around, so that's 0 to 2 pi. Okay, and what is z? Z, you can see from here, is r cos theta. Okay, so now we can separate the, okay, let me write it again. 1 over m, integral 0 to pi, integral 0 to pi by 2, 0 to r of rho times r cubed sine theta cos theta dr d theta d phi. And you can see again this is going to separate, right? R integral and theta integral separately. So what's this? Well, first of all, what's m? M again is the density times the volume, and the volume of half of a sphere is 2/3 pi r cubed. So this gives you 3 over 2 rho pi r cubed. And we can separate the integrals. Integral from 0 to 2 pi d phi, integral from 0 to pi by 2 sine theta cos theta d theta, okay, and integral from 0 to r cubed dr. Okay, so continuing with this then, again, rows, I forgot about rows cancel. This gets you 3 over, and this integral just gives you 2 pi, so that cancels the 2 pi here. So you get 3 over r cubed, the integral from 0 to pi by 2 sine theta cos theta d theta, integral from 0 to r cubed dr. So this one, if I say that u is sine theta, then this becomes, so u is sine theta. This is the integral from 0 to 1. du is cos theta d theta. So that just becomes the integral of u du. And this one is integral from 0 to r cubed dr. So this one is a half, and this one is r to the 4 over 4. So putting all that together, you get 3 over r cubed times r to the 4 over 8, which is 3/8 r. Okay. So on the hemisphere here, the center of mass is 3/8 of the way up. Here. Okay. So part C is the shell. So if I go back, the pictures for part B and part C are the same. The difference is in part B you imagine this is solid, so you imagine it's a solid hemisphere, but here you imagine only the shell, like a kind of eggshell. So there's nothing inside here, just only the surface around the outside. Okay. So the difference here is here you need to integrate over r. So r goes from 0 to capital R. But here, r is fixed. It's just equal to capital R, right? Because you've only got the surface. So it's exactly the same integral, except you don't have the r integral, right? If I go back to here, this is the integral we got for the solid. The only difference is that you don't do the r integral. You just replace small r with capital R. So this gives you 1 over m, integral from 0 to 2 pi, integral from 0 to pi by 2, over from here rho, and then just capital R cubed, sine theta, cos theta, d theta, d phi. Okay, so that's the only difference, is that this changes to that. Okay, and the mass is rho times the surface area, and the surface area is 2 pi r squared. So that gets you 1 over 2 pi r squared, integral from 0 to 2 pi d phi, integral from 0 to pi by 2, sine theta, cos theta, d theta. This one we just worked out was a half. This one gives you 2 pi. And there's r cubed, sorry, which I forgot about r cubed. Okay, so 2 pi's cancel, and you just get r over 2. Okay, so this is an interesting result. For the shell, just only the surface is there, the center of mass is exactly halfway up. Okay, that's what you've shown there. And finally, part D, we're looking at this cone here. Okay, so we're going to use the coordinates r, theta, and z, and the volume element dv is same as for polar coordinates r, dr, d theta, and then you have to multiply dz as well. Okay, so we have that the center of mass of the cone is 1 over m integral of rho times c times the volume element, and we said the volume element is r dr d theta dz. And now we have to work out the limits of the integrals. So if I draw the cone here, okay, and we'll say that at the bottom of the cone the radius is capital R, like we have been saying. And let's say that the height of the cone is h, and that means z goes from 0 to h, theta goes all the way around, so that's 0 to 2 pi, and r is a little bit tricky, because at the bottom of the cone it's capital R, but as you go higher up it gets smaller, right? So that means that the integral limits here is a function of the height z. In particular, if we're at height z here, then the length here, you can check, should be equal to capital R, 1 minus c over h. Right? Because when z is 0, it's capital R, and when z is h, it's 0. So this is 0, R, 1 minus c over h. So this is something I actually haven't talked about yet. Here you see the variable z appears in the limit of the integral on R. And this means that you have to do the R integral first. Okay, in the other cases we've done so far, all of the integrals were separable. So you could do the R integral separately, theta integral separately, and so on. But in this case, because there's a z here, you have to do the R integral first, before you do the z integral. Okay. So also we know that the mass of a cone, well, you may not know, but the formula is it's a third times the area on the bottom, which is pi r squared, times the height of the cone h. Okay. So putting all this together, you get this is 3 over pi r squared h. Density here cancels the density there. So we can separate the theta integral because nothing depends upon theta. And then you've got the r and z integrals together. Z integral from r minus c over h times r dr dc. Okay, so this theta integral just gives you 2 pi. So this gives you 6 over r squared h times the integral from 0 to h c times this, which is r squared over 2, 0 r minus c over h dz, which is 3 over h integral from 0 to h of z times 1 minus c over h squared dz. Okay, so that's now an integral we can do. If I say u is 1 minus c over h, then du is minus dz over h, and when c goes from 0 to h, u goes from 1 to 0, and then z is 1 minus u times h. Okay, so here you get 1 minus u times h times u squared, and dz is h du. Okay, so neatening that up a bit, that is 3h integral from 0 to 1, 1 minus u, u squared du, That's 3h u cubed over 3 minus u to the 4 over 4, 0 and 1, which is 3h a third minus a quarter, which is a 12th. That's 3h over 12, which is h over 4. Okay, so the centre of mass is a quarter of the way up the cone there. Okay, right, so that's the end of this worksheet. As I said, the only thing that's going to be on the exam is the first 3 questions. Okay, so finding the gradient, Taylor series, and second derivative test will be on the exam. The rest of it is not on the exam, but it is going to be useful for you in physics, so it's worthwhile to look at anyway. Right, so that's it. I wish you the best of luck, and hopefully I'll see you next week.